So here's an example where we're given a simple circuit. We have two voltage supplies here, and they're asking us to find this current IL, which we see here is flowing through resistor RL. And they're asking us to solve this using Thevenin's theorem with respect to terminals A and B. So that's these terminals here, A and B. So what that means then is we need to consider this circuit without RL being there. And so what does that mean? That would mean we would need to go ahead and act as if this circuit's not here first and find the Thevenin equivalent between A and B. And then come back and add RL back in to solve for this equation. So the first thing we can do then is we can look for the Thevenin resistance. So remember, when we do the Thevenin resistance, we short out voltage sources and open current sources. So in this case, we could short out both of these voltage sources. So it'd be as if they're not there. And then we would replace those with a short circuit, like so. And so now we need to find our Thevenin, which would be the resistance between those two terminals if we were to take an ohm meter and put both leads on A and B. So we could redraw this a little bit, and what that would look like then is really what we would have then is R1, and then we would have R2, and then we have A and B. So this is the same circuit as what I'm showing over there, but this is a little easier to visualize it. So now we're looking for this resistance looking back into here. And so our Thevenin then, we can see from this diagram, is simply R1 in parallel with R2. So we can write that then as 3 times 12 over 3 plus 12. And so when we calculate that, that gives us 2.4 ohms. So there's our Thevenin resistance between A and B. So the next thing we need to try to do is figure out what the open circuit voltage would be. So to do that, let's go back and reset our circuit here. So again, we're acting as if this is open right now, but there's nothing here. We'll come back and put that in place once we have the Thevenin equivalent. But now we need to know what the voltage would be across there. And so what that would be then is our, since we're using E for sources, we'll call this E Thevenin. And that's across here. We need to know what the voltage source. So in other words, if we brought a voltmeter and put it there, what would we measure? Well, to find that out, we're going to have to first solve for what the current flow is in this circuit. And so we'll just call this I total, or IT. So what's the current flow? And it'll flow all around the circuit here, right? So we have a closed circuit here. It's the same current flowing there. And so to solve for that, it's just an Ohm's law application. So IT then in this case would just be the total voltage around the loop over the total resistance. With the total voltage, we can see that in both cases, E1 and E2 are, that should have been 21 volts. E1 and E2 are both pushing the current around the loop. And so in that case, the voltage will just be E1 plus E2. And then the total resistance is just R1 and R2 in series, right? So that's just R1 plus R2. So if we plug in the values for this, we get 42 plus 21. That's our two voltage sources. And then we'll have 3 plus 12. That's our resistances. And so when we calculate that out, we should get 4.2 amps. So that's what the total flow around that circuit should be when we're open between A and B. So now we should be able to come back and do a voltage loop analysis. And so we're going to do our loop. Let me highlight what we're going to do here. We're going to do this loop here. And remember, any loop we pick, the voltage around that loop should be equal to 0. It's got to equal to 0 because energy has to be conserved. So that being the case, the voltage ETH has to equal whatever the voltage drop is across the rest of the circuit. So as we come around this circuit, the first component we see, of course, is our ETH. And so we'll say our Thevenin, which will eventually be our voltage open circuit, however you want to call it. Same thing. That's got to equal to the voltage drop across the rest of the circuit. So when we look at the rest of the circuit, first one we have is, let me get my colors right here. First one we have, we'll put in green here, is this R2. And so remember that we have that IT still flowing through it, right? So let me write that back. We still have IT flowing in this circuit when it's open circuited. It doesn't go through the ETH, but it goes through these two components. And so that being the case, the voltage drop across R2 will just be IT times R2. And then, of course, we have a voltage source. So as we come around this way, we see we hit the minus sign first. So it'll be minus E2. And so we can plug in values for that now. And when we do, we should have 4.2 amps times R2, which is 12 ohms. And then it should be minus 21 volts. And so when we calculate that out, we're going to have 29.4 volts. So that's our Thevenin voltage, or open circuit voltage. So now we have our Thevenin resistance and we have our Thevenin voltage. So we can redraw this circuit with nothing connected between A and B. And when we do, what we have then is we have our voltage source. Remember, our Thevenin equivalent circuit just is simplified down to a source and a resistance. So we still have our terminals A and B. Let me put that above it. A and B. And so we're saying that this is 29.4 volts and that this is 2.4 ohms. Volts. So that's our equivalent circuit for what we have up top. And so just to reiterate, make sure we understand, again, if we take out what's in the middle here, this is what we could replace it with. So we can replace between A and B with this circuit here. So here's our A and B. So those should be the same thing. So if we put a voltage meter there, we should measure 29.4 volts between A and B. And then if we were to measure the resistance with the voltage sources shorted, that should be the resistance. So now to solve the original question, we have this resistor now that we are putting across there. Let me get my line and weights right. So we have this resistance here that we're connecting to A and B. And this is what we saw up here. This is our RL. Equal to 6 ohms. And what we're asked to solve for then, again, is this IL. So we're asked to solve for this current IL flowing through that resistor. Well, because this is just a single loop, IL is going to be flowing through the whole thing, right? Through the whole circuit. So now this just becomes a simple Ohm's law equation. So we're solving, again, for IL, which again is just the voltage over the resistance in our circuit. So in this circuit, our voltage is 29.4 volts. And then our resistance is just two resistors in series. So we just add those together. So it'll be 2.4 plus 6. And so when we solve for that, we come up with 3.5 amps. And so this is the solution to the problem. IL here is 3.5 amps, but this is how we solve it using Thevenin analysis.